Hi everybody, in this video we're going to go over the first section of chapter 7, and in this section we are going to talk about the most fundamental of trigonomic identities. So here we are. Now first thing, what is an identity? Well, if you recall from college algebra, I think this was probably one of the first or two sections, an identity is an equation that is true for every value in the domain of its independent variable. For example, x minus 1 is equal to 1/4 times the quantity 4x minus 4. Well, as you might guess, that's an identity. It was actually true for every single value of x on the real line, and we could say that this is really a trivial identity. Well, it turns out that we have statements involving trigonometric functions which are true for every single value of x or theta in their domain. And here, all of these we've actually seen before, and we're just going to review them again and then apply them in this section. Of course, the first collection of identities we talked about were the reciprocal identities, where cotangent is the reciprocal of tangent, because cotangent, once again, is x over y, and tangent is y over x. Secant is reciprocal of cosine, and cosecant is reciprocal of sine. And furthermore, since tangent of theta is equal to y over x, or we could say y over r divided by x over r, it turns out that this is equal to the quotient of sine theta over cosine theta. And similarly for cotangent, we have cosine over sine. The other identities that we presented in the first part of chapter 5 were the Pythagorean identities, where we had sine squared plus cosine squared is equal to 1, and we had tangent squared plus 1 is equal to secant squared, and we had 1 plus cotangent is equal to cosecant squared, and those can all be derived by starting with the equation x squared plus y squared is equal to r squared, and if you divide everything by r, you get this one. If you divide everything by x, you get this identity, and if you divide the entire equation by y, you get this identity. And then in chapter 6, when we were plotting sines and cosines and tangents and cotangents and secants and cosecants, we noticed that sine is an odd function, that cosine was an even function, and that tangent was also an odd function. And as a consequence, they satisfy these identities. And then since sine was an odd function, its reciprocal would also be an odd function. And since cosine was an even function, its reciprocal would also be even. And similarly, since tangent was an odd function, cotangent is also an odd function. And notice here that we can take the Pythagorean identities and we can manipulate them to solve for various values, which will give us alternate forms for each of the Pythagorean identities. So that right there is a summary of all the fundamental identities, and we are going to use these along with other tools to solve problems. And here is the first one. Here we have that cosine is equal to 5/8, and theta is in quadrant 4, and we need to find the following function values. And the first one is sine of theta. Now notice if theta is in quadrant 4, then we know that the sine of theta is going to be negative. It's going to be less than 0. And there's actually two ways to approach this. One is using the identities, and the other one that we just discussed, and the other one is just using the original definition of cosine and sine. So let's start off with the identity approach here. Notice that we have cosine is equal to 5/8, and we know the Pythagorean identity, which is that sine squared of theta plus cosine squared of theta is equal to 1. And if that's the case, then one of the alternative identities would be that the sine squared of theta is going to be equal to 1 minus cosine squared of theta. All right, well, cosine theta is 5/8, so cosine squared theta is going to be 25/64. So this is going to be equal to 1 minus 25 over 64. We can write that as, well, we can express 1 as 64 over 64 minus 25 over 64, and that will give us 39 over 64. And once 64, then that should be a 9. There we go. And once again, that is equal to sine squared theta. Of course, we need to find the sine of theta, so we're going to take the square root. Since we're in quadrant 4, we know that sine is strictly less than 0, so we are going to take the negative value of the square root, and that means that sine of theta is going to be equal to the negative square root of 39 over 64. Well, it turns out that the 39 can't be simplified. The only factors of 39 that I can think of are 3 and 13, both of which are prime numbers. So this cannot be simplified. So in the numerator, we're going to have negative square root 39, and of course the square root of 64 is 8. And that would be your answer using the identities. So on this side, we use the identities. Now, the other way to approach this is to use the original definitions for cosine and sine. And if you recall that the cosine of theta on the Cartesian plane is going to be the ratio of the x-coordinate over the distance between the point and the origin and the point. And the sine of theta is going to be the ratio of y over r. So and also notice that we are in quadrant 4, and that means that x is going to be greater than 0 and y is going to be less than 0. Okay, well, since cosine of theta is equal to x over r, or is equal to 5/8, then one value for x is 5, and then one value for r is 8. So all we need to do is figure out what y is. And based upon the Pythagorean identity, we have that x squared plus y squared is equal to r squared. So we can rewrite y squared as r squared minus x. And then since we're in quadrant 4, y is going to be equal to negative the square root of r squared minus x squared. I forgot the squared over here. And doing the substitutions, we will have the square root of 64 minus 25, which will give us the square root of 39. I'm sorry, and remember taking the negative square root, so this will be negative root 64 over 25, which will give us the negative square root of 39. So if that's the case, then we have that sine of theta is equal to y over r. Well, y is negative root 39, and r is 8. And there you go. You have the exact same answer. On top of this, what do we have over here? Well, now we know what x is. X is 5. R is 8. And y is negative root 39. And since we know these three values, we can at least solve any, we can find all the 6 trig functions for this particular angle, which makes part B a snap for us. So using the definitions, now we know what x, y, and r are, we can actually figure out what tangent of theta is using the original definitions. And the tangent of theta is nothing more than y over x. Well, y is negative root 39. X is 8. There you are. You're done. Now over here, it is just as simple, because remember the quotient identity for tangent is sine theta over cosine theta. All right, well, what is sine theta? Sine theta is negative root 39 divided by 8. What is cosine theta? 5/8. Okay, well, the 8's in the denominator cancel. If you don't see it, you can actually multiply the entire fraction by 8 over 8, and then they'll cancel, and you will have that tangent of theta is equal to negative root 39 over 8. Now, as far as secant of negative theta is concerned, there's really no good way to do that from the definitions because we have a different argument. So here, we want to take advantage of the fact that secant is an even function. This bad boy is even. Well, that means that secant of negative theta is equal to secant of theta. Okay? Using the reciprocal function, hey man, that is 1 over cosine theta, which will be 1 over 5/8, or 8 over 5, and there you go, and you're done. Of course, once you have that, of course, on this side, once you still need to use the even odd identity. So we would have that secant of negative theta is equal to secant theta. But once you've done that, we know that secant theta is equal to r over x. R is 8 and x is 5. So you can still do it using the definitions, but you still need to use the even. You still need to recognize that secant is an even function and take advantage of that. So that is our first example. Here is our second example, and once again we're going to do this in two ways. The first way is using the identities. Now we want to write tangent in terms of cosine. Okay, so the first thing we can do is realize that, well, the we can use the quotient identity, and we have that the tangent of x is equal to sine divided by cosine. Probably need to conclude the argument there. Okay, but now we need to get sine in terms of cosine, and we can use the Pythagorean identity to do that. We have that sine squared x plus cosine squared x is equal to 1. Therefore, sine squared x is equal to 1 minus cosine squared x. Or that sine of x is equal to plus or minus the square root of that. So we have that sine of x is equal to plus or minus 1 minus cosine squared x. We can actually take this right here and we can substitute it back into here. And if we do, we will have that the tangent of x is equal to, instead of sine x, we're going to have plus or minus the square root of 1 minus cosine squared x all over cosine of x, and you are finished. Okay, now how could you do that using just the definitions? Okay, well, the tangent of x is equal to y over x, and we can write y as the square root, or as plus or minus the square root of r squared minus x squared all over x. Now where do I get that? Well, remember, x squared plus y squared is equal to r squared. So y squared is equal to r squared minus x squared. Therefore, y is equal to plus or minus the square root of r squared minus x squared. So that's where that comes from. Now, what we can do now is we can actually factor out that r squared. And if I do, I'm going to have that the tangent of x is equal to plus or minus the square root of r squared times 1 minus x squared over r squared, all that divided by x. And now what I can do is factor out that r squared, and that will give me plus or minus r times the square root of 1 minus x over r, the entire thing squared, divided by x. And now I can multiply both sides, or I can multiply this fraction by 1 over r over 1 over r. And if I do these cancel, I will have that the tangent of x is equal to plus or minus 1 minus x over r, the entire thing squared, divided by x over r. And what is x over r? Well, x over r is cotangent. So this is going to be equal to plus or minus 1 minus the square root, plus or minus the square root of 1 minus cosine squared x. I'm using x in two different contexts, which I know is a problem, divided by cosine of x. So once again, it can be done in two ways. Which way is probably the better way to do it? Probably using the identities. The definitions here, whether it's definitions here doing the derivation is actually kind of clunky. But hey, if you forget the identities, just notice that there still is another way to do it, which is the main reason why we're doing both ways here. Okay, this brings us to another problem, and it is this one. Here, we want to write 1 plus tangent squared theta over 1 minus secant squared theta in terms of sine and cosine, and then simplify them so that no expressions, no quotients appear. So the first thing is to write them in terms of sine and cosine. And once we've done that, we want to simplify them so that there are no quotients. Now, sometimes to do the simplification, we are going to write our answer, not our final answer, not in terms of sine and cosine, but in terms of something else. But basically, we have two steps. One expressed in terms of sine theta and cosine theta, and then 2 simplify so that there are no quotients. So once you finish 2, your answer may not be in terms of sine theta and cosine theta. That's the primary point that we have here. Okay, so how can we do this using the trigonomic identities? Okay, well, notice that recall that one of the Pythagorean identities is that 1 plus tangent squared theta is equal to secant squared theta. Okay, if that's the case, then we can write this as secant squared theta divided by 1 minus secant squared theta. Okay, now we are asked to express this thing in terms of sine and cosine, and of course we know that secant is 1 over cosine. So we can write this as 1 over cosine squared theta divided by 1 minus 1 over cosine squared theta. Okay, so we've done the first part. We actually have this written in terms of sine and cosine. We're done with the first part. Now we need to simplify so that there are no quotients. So how can we do that? Well, the first thing that we can do is multiply this by cosine squared theta over cosine squared theta. And if I do, this cosine squared theta cancels with that. And what we will have is, well, we'll have a 1 in the numerator. We will have cosine squared theta right over here in the denominator, cosine squared theta, and then minus, and then cosine squared theta over 1 over cosine squared theta. That's just going to be minus 1. Now what we're going to do, if we factor a negative 1 out of the numerator, we are going to have 1 divided by negative 1 minus cosine squared theta. Okay. If that's the case, we can use our Pythagorean identity for sines and cosines, and we can rewrite that as negative 1 over sine squared theta. And then to get rid of a quotient, we can recognize that sine squared theta can be 1 over sine squared theta can be written as cosecant squared theta, and that will give us our final result of negative cosecant squared theta. So here we are We have no quotients. It's been simplified so that there are no quotients, and our answer is actually cosecant squared theta, which is what we're looking for. So just keep in mind that once we simplify, you may not have sines and cosines, which is perfectly fine. That's what we're looking for. In this particular example, it's probably best to use the identities because we have these negative angles that we have to resolve, and we need to use the odd-even identities to do that. Now notice here that sine is odd. So sine of negative theta is going to be equal to negative sine theta. Cotangent is also odd, so cotangent of negative theta is going to be equal to negative cotangent of theta. But cosine is even, so cosine of negative theta is going to be equal to cosine of theta. So let's go ahead and write this down and apply the odd-even identities. Now since sine is odd, sine of negative theta is going to be equal to negative sine of theta. And since we're squaring this, we want to square the entire quantity. So notice how I write this out to make sure that I include the negative sign in the square, because once again, we want to square the entire thing, and if I had the 2 here, we would be neglecting the coefficient. Similarly, cotangent of theta is going to be equal to negative cotangent of theta, and we want to square the entire thing. Now cosine of negative theta is just simply cosine of theta, and we want to square the entire thing as well. We don't need to do this for an even function, but just to be consistent with all the other ones. And this is probably the safest way to do it. We're going to basically write it like this. And now we can evaluate each function. The square of negative sine theta is going to be positive sine squared theta. The square of negative cotangent theta is going to be equal to cotangent squared theta. And of course, the square of cosine theta is just cosine squared theta. Now we can rewrite this as sine squared theta plus cosine squared theta plus cotangent squared theta. And notice that this right here is a Pythagorean identity, and that's going to be equal to 1. So since this is 1, we can write this as 1 plus cotangent squared theta. Now we can use the reciprocal identity, because cotangent squared theta, or cotangent of theta, is equal to cosine of theta divided by sine of theta, the entire thing squared. And of course we can evaluate this, and if we do, we're going to have 1 plus cosine squared theta over sine squared theta. Okay, now remember, and look, and now we actually have this, we have now written this in terms of sine and cosine. Of course we did it back here, but this is probably a cleaner version. Now we need to simplify this, so that part is done. Now we need to simplify this so that we have no more quotients. Now the first thing we might want to do is give ourselves a common denominator. We can do that by writing this as sine squared over sine squared. So we will have sine squared theta over sine squared theta plus cosine squared theta over sine squared theta. And you can probably see how this is going to play out with a common denominator. We can write this as sine squared theta plus cosine squared theta all over sine squared theta. Okay, well, turns out that using the Pythagorean theorem, the Pythagorean identity, same one we used here, that's just 1. And we have 1 over sine squared theta, and we can get rid of the quotient by writing this by noticing that secant is 1 over the sine, and that will give us our final result, secant squared theta. So there's our identity. And this right here is our final example. And here we want to write secant in terms of sine. And once again, there are 2 ways of doing it, but let's just go ahead and use the identities. Now notice that secant, we can write secant in terms of cosine. Secant of x is equal to 1 over cosine of x. Of course, and we also have the Pythagorean identity between sine and cosine. We know that sine squared x plus cosine squared x is equal to 1. Therefore, cosine squared x is equal to 1 minus sine squared x. Or cosine of x is going to be equal to plus or minus the square root of this. 1 minus sine squared x. Therefore, we can write secant, and we can write secant of x as 1 over plus or minus the square root of 1 minus sine squared. And that is all I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.